today, I've decided that we are not going to continue on with that chief cohomology stuff. It's just a little too much at this point. The reason I wanted to do the X stuff ahead of time is it turns out to be really useful and interesting when applied to primary decomposition things. And so that's why I wanted to do that first. But then I kind of on a little off the deep end, and we can maybe do some of that later in the semester. Instead, what I'm going to do is start in on primary decompositions today. So today we're going to, probably today and next time, which will be the one after next, we'll all be on primary decompositions and computing primary decompositions. Okay, so let's talk primary decompositions. I'm going to sort of do some of the actual math part of a primary decomposition. I'm going to do it as if I'm going to define everything, but it might be a little fast if you've never seen it before. But I have some good exercises on this Jupyter notebook that it's posted, and it's also here for you to take a look at. So here, what's the idea? The idea is we're given an ideal I inside of R.
The camera, please.
Yes. Thank you. Okay, so we have an ideal in R, I in R. Now, the whole game of this, we're eventually going to, eventually, we're going to set R to be various rings. It will be like x1 to xn, so e.g., we'll take this one. But for now, the whole thing works really nicely if R is just a Noetherian ring. So every ideal is finitely generated, all that kind of stuff. Okay, and the idea is we would like to understand I. So understand I. This is an extremely vague notion. In fact, the whole field of commutative algebra would be gone if we have already solved this problem, probably. Okay, so anyway, so we want to understand I. This oftentimes, in general, whenever you have some objects you want to do it, you might want to break I into easier pieces, into simpler pieces. We also might want to consider the zero set of I, except that actually we haven't defined this. We're doing this more generally right now, but we might also want to understand an algebraic set X contained in some affine space, affine n space. Okay, and then this thing, e.g., we might have X is equal to the zeros, where let's say the variables here are x1 to xn. And we might have like x1, x2, ... xn equals 0. And this thing here is this is a really simple one, but this is equal to the zero set of x1 equals 0, union ... union xn equals 0. So these are much simpler pieces. Well, this is pretty simple. Okay, but nonetheless, these are simpler. These are nice linear objects. Can you see that from back over there, or should I not write so low? Yeah. Let me just do that. I think for the moment I don't need that. Okay, so we want the simpler pieces. So what are the simpler pieces? Oh yeah, and everything we're going to be doing is we're going to consider this as a proper ideal. So we don't really care what happens with the one. The zero set of one is the empty set. It's kind of an uninteresting object for the most part. Okay, so there's a few different notions for definition that are all at this level of generality. So definition, I, let's do these in several groups. I is maximal if there does not exist sort of I contained in J contained in R, where this is not equal and this is not equal. Okay, There is no proper ideal larger than it. So it's a maximal proper ideal. B, I is prime. These are the most important ones. I is prime if whenever fg is in I, then that implies that A is in I, except I'm using different notation than I have here. Too bad, F is in I, or G is in I, or both. But in any case, we have that. Here's another thing in the whole game of primary decomposition. I is primary. This is pretty good though, that if you could actually scan through all the elements of I and you see any that factor, you know that that one or the other has to be in a prime ideal. So you can, these are really good, but not all ideals are like that. So here's an example of one, or a type of ideal that is not quite as good as that. If fg is an I, implies f is an I, or g to the m is an I for some m natural number. Okay, this is not very symmetric, but you get to choose as the person using this condition which one is f and which is g. Okay, so it's not like one of them is in it and the other one. I can say f of g is an I, so I can flip this too. So I get lots of conditions here. Okay. Here's another one that's kind of interesting. I is irreducible. You don't see this one too much, except in for some kinds of ideals, like monomial ideals. If I cannot be written as a I equals I1 intersect I2, for I1 and I2 both not equal to I. In other words, these are both have to be larger than I, just because of the intersection is equal to that. And if you can write it as an intersection of larger things, then it's called reducible. Otherwise, it's irreducible. You have to be really careful. This is a weird. Irreducible, it does not mean what you think it means as far as geometric. We have irreducible varieties and things like that. This is the very algebraic use. So warning. This is not the notion of a zero set, say of V of I, which we haven't completely defined in this generality, being irreducible. Okay, so you have to be kind of careful with your language here. But for ideals, we can have these kinds of things. Actually, irreducible is going to essentially be prime ideal. So you might think that it would be nice to have a slightly more consistent notation, but this stuff was done in geometry and it was done in like number theory, and they had different notions before they got put together. Finally, I is radical if g to the m in I implies that g is an I. And remember, we already defined the radical of I. It's the set of all g's such that g to the m is an I. So this is i.e. I is equal to the radical of I. So it's a radical idea. Okay, so these are all 5 notions. Yes. Yes.
There's the notion of the ideal I being irreducible, and there's the notion of the zero set of an ideal being irreducible. Are there any implications one way or the other?
Yes. So if this is irreducible, if I is irreducible, then if you think of V of I as being just the zero set, in other words, you don't worry about the multiple, just chapter 1 of Hartshorne kind of zero set, not doing schemes and things, then this thing will be irreducible. It would, but in fact, all of these things have relationships here. And
all I'm really comfy with is affine varieties right now.
Right. So if I is an ideal in k of x1 to xn, and then irreducible, we're going to see examples of it in a bit. But the zero set being irreducible and this are here's the thing is that it's except for one kind of ideal, it's really kind of not so easy to see these irreducibles. And they're not when if I can write it as the intersection of things, it might not be unique at all. So I have all sorts of issues with that, which is why we tend not to. We could talk about an irreducible decomposition of I, which is I is an intersection of irreducible ideals. And so actually we're going to do that in just a bit. But before doing that, let's do a couple examples of this. So
Mark, sorry, before going
yes.
up, do you know what are the information for getting into the Zoom since guide
There's a password now.
yeah, there is and also the link that they put on the website. I think
It doesn't have the password anymore.
yeah.
There was an email with the password.
Yeah, but I am thinking it was you registered to the email as
Oh,
Does
I
anyone-
disabled the
email?
wait list.
It's what?
I just disabled the waiting room, so right now people can join in, but I'm monitoring.
Okay, good. Okay, thanks. You've got it. Okay. I don't know if we should say it in at the maybe we don't right now, but anyway, I don't know what the problem was with it, but hopefully everyone is the person able to get in now.
I asked. I say that
Yes,
now.
I'm letting people in, whoever's joining.
Okay, thanks.
Sorry.
Okay, no, it's okay. So there's a few things here. I have a few exercises on this sheet that I've handed out or online. You can find it in the usual place for the thing. Is that so let's talk about. I'll do this as an exercise, but we'll talk about it just a little bit. So this is a good one to do. So consider monomial ideals. In K of x1 to xn. Okay, so just ideals that are generated by monomials. Okay, so the first thing is, which are maximal? Which are prime? Which are irreducible? And radical. Okay. If you have not seen this before, this is something that we will do perhaps at the that you can do in when we do projects stuff. Okay. Now let's and also which are primary. I'm going to just give you some examples of ones that are maximal. X1 to xn is a maximal ideal. Okay. I don't mean maximal in terms of monomial ideals either, although actually it does mean that, I guess. Maximal ideal. What's a prime ideal? How about x1, x3, x5? That's a prime ideal. What's an irreducible ideal look like? That's actually something maybe I'll let you take a look at. Okay. And a radical ideal. So whenever you have a monomial and you take to some power, then the monomial itself is in there. So this would be an example would be x1, x2, x1, x3, x4, x2, x7. Okay. Oops, angle brackets. But anyway, so there's that. And so interesting question is which ones are irreducible and which are primary? But basically, radical ones are going to be pretty easy. They're square-free monomial ideals. They're monomials generated by square-free monomials. Maximal prime monomial ideals is one. This one here. You can think about it, and you can figure out which ones are prime. Those are pretty straightforward as well. But irreducible and primary are a little bit more interesting. Okay. Some things to note. So some facts that you can either think about. I have it down as exercises, but if you might know this already. One of them is a maximal ideal. So I maximal implies that I is prime. Okay. So here's another one that is actually important, and maybe we'll talk about this. I primary implies that the radical of I equals P is a prime ideal. Actually, that somehow should make sense. If I have a primary ideal and I take F times G in here, and that's also in the radical, so F is in the radical or G is in the radical. I mean, that's exactly the primality condition. So I primary implies that the radical of I is prime is good. Actually, and then what we do is we say that we usually don't use I as a primary, we use say Q or something like that. But anyway, I is called P primary. If I is primary, and the radical of I is equal to P. Okay. So these are going to be the prime ideals, and these are the main things that we're dealing with. Here's another fact. So here's a question, actually. Suppose I is an ideal. And the radical of I is equal to P is equal to a prime ideal. Okay. Is I primary? Is I P primary? Okay. You can consider the following ideal. Consider I equals x squared, xy. The radical of I is x because x is in there and xy, so that's the only thing. By the way, you need to. There is a little bit more going on with this. How do you check that something is a radical ideal? You have to take any polynomial and take a power of it and see if it's in there. But the point about a monomial ideal is if you have a polynomial in the ideal, that's equivalent to all the monomials being in the ideal. So you have to, if you haven't thought that through before, it's important to sort of make sure that you're not just sort of blowing through and doing it. There's actually something to be proved here, that you don't have anything else. But it's an easy fact of that. Anyway, so this is such an ideal. I is an ideal that is P primary. Sorry, I is an ideal whose radical is prime. So I'm going to leave this question for you, but the answer is no. And but an ideal I such that the radical of I is prime is called, or we will call it, a pseudo primary. Okay. It turns out that when we're doing a computation of primary decompositions, which we haven't defined yet, where you will come across ideals that we are hoping are primary, but we don't know if they are or not. And so we have to either prove that they are or split it somehow. And that's what's going to happen here. By the way, another exercise that is an important one is the intersection of two P primary ideals is again P primary. Okay. Now what we want to do is we're going to first of all do irreducible decomposition. And what the result here is proposition. Every proper ideal. By the way, maximal ideals, you would think that the unit ideal is a maximal ideal, but we're looking at ideals that are not the unit ideal. This is otherwise that isn't so useful. But at any rate, so every proper ideal in R, in R is a finite intersection of irreducible ideals. So I is equal to, let's say J1 intersect J2 intersect ... intersect J some number. We don't know how many. Okay, where each J sub I is irreducible. I haven't even given you a single example of an irreducible. I should probably do that. X1 squared, X2 cubed is irreducible. Okay, so the kind of thing is that if you have a factorization inside of an ideal, then and that neither of the terms is in it, then maybe you could add F to one of the elements and G to the other element, if F times G is in there. Yeah.
How do you think of irreducible?
I don't know.
Always have geometric.
I'm not really sure, to tell you the truth. It's used as a quick proof that we have a primary decomposition, but it's just on the way. It does turn out to be useful for monomial ideals. So they're going to look perhaps similar to this kind of thing. But yeah, but this kind of way of getting a decomposition is going to be useful in other ways. Yes, question?
Sorry, this might be a silly question.
Yeah.
Why is thinking about having your ideal be the intersection of two larger ideals? Why does that being the case mean that you can reduce your ideal?
Yeah, no, that's a good question. So the idea is really that it's like it's like take a number and multiply and write it as a product of prime numbers. Prime numbers are considered to be the building blocks. So you can get all the other ones by multiplying those guys together. Here, it's not so much that it's going to be a part of it. You're going to get all these prime ideals and primaries, and everything can be written as an intersection of those things. So it's not as good as that, but in fact, this is one of the things that who did it? Probably Kronecker. There were all these extension fields where you didn't have unique factorization, but if you thought about it in terms of ideals and primary decomposition, then you did. So that was where it came in from there. But then it also had to do with geometry. Like this is going to be this ideal here, x1 to xn. Oops, not that. Just a single element there. That's an ideal, and that is equal to the ideal x1, intersect the ideal x2, intersect to the ideal xn. Okay, and these are simpler ideals than that. And this makes it look that an intersection of ideals is not so bad, but in fact, it can be extremely difficult if these are not all binomial things.
This is sort of related to like inclusions and intersections swap when you go from the geometry to the algebra.
A little bit, yeah. So how do we prove this? Let's do it. It's pretty straightforward, but it's worth thinking about because we're going to be interested in decompositions of I as an intersection of prime ideals or primary ideals or things like that. Not so much irreducible, but this is a good way to get started. So if I have I and it is either irreducible or it's not, right? Suppose it's not irreducible. This is going to be a schematic. If it's not irreducible, if I is equal to I1 intersect I2, then I'm going to write this I1 here and I2 here. And this line means that I, the one above it, is equal to the intersection of these two. And actually, these are not equal. So this is contained in here, but not equal. This is contained in here, but not equal. Does that make sense? So this is if this and I1 is not equal to I, and I2 is not equal to I. Okay. So if I is not irreducible, we can break it up into these two larger ones. Okay. And now we take a look at I1. Is it irreducible or not? Who knows? But if it is, and suppose we have an oracle that tells us what that is, we can maybe break this down into the intersection of two other ideals. Let's call this I11 and I12. So the first index is that one, and the second index is the next guy here. And this is going to be contained inside of here, and this is going to be contained inside of here. And this is if I1 is not equal to an irreducible ideal, then I1 is equal to I11 intersected in I12. Okay, does that make sense? We're going to do that, and now we can do the same thing. This is either irreducible or not. If it's not, then we can go like this, and we're going to get this is not contained but not equal, and this is going to be I2 1 and I2 2. It's a nice binary tree. Okay, but it will stop. There will be a leaf when you have an irreducible ideal, and otherwise there won't be. So what's the problem here? And what's true too is that I is equal to the intersection of these two, so it's an intersection that is equal to all four of these. So in fact, it's always we have I is equal to the intersection of all the leaves, of all the leaf ideals. So big deal. Why can't this keep going on infinitely far? So we could keep going here, and maybe this is going to be I111, and this is I112, but maybe this one is not, and maybe this is an infinite sequence all the way down here. So we have an infinite tree. It could happen, but it can't happen here. Why not? R is Noetherian, and we see just visually all these increasing ideals. And so eventually it has to stabilize, which means you can't go any further. So this tree is finite since R is Noetherian. And therefore, once it's finite, then I is the intersection of all those finite number of leaves. And therefore, I is equal to the intersection of all the leaves, which are finite in number. All the leaf ideals, maybe I should say. Ideals at the leaves. And we're done. Okay? Does that argument seem okay to everyone? We can do this whenever we have a way of taking an ideal and splitting it into making it into two larger ideals. And so this works for this one, for irreducible ideals. So we always have an irreducible decomposition. Now, here's a definition. A primary decomposition of an ideal I, of I contained in R, which is not equal to R, is a representation I is equal to Q1.
The camera.
Oh yeah, sorry, thanks. Okay, so primary decomposition of an ideal I is a representation I equals Q1 intersect Q2 up to some number of these guys. What am I using here? R. Okay, where each Q sub I is I'm going to say P sub I primary ideal, just because it's nice to have the names of the prime ideals that are there. So each one of these things are primary, therefore their radical is some prime. That's this. This is a P primary ideal. Okay. A primary decomposition is kind of nice, but in reality, there could be a whole bunch of these with the same PI. And there could also be a whole bunch of ones that aren't needed in this. So this is an irredundant decomposition. Primary decomposition. And I'm going to call that PD. Okay, irredundant primary decomposition PD. If also, well, it has to be all primes. If all primaries. If also one, the P sub 1 up to P sub R are distinct primes. In other words, are pairwise distinct, say. So they're all different. And 2 is that I is not equal to the intersection of any fewer of these guys. So QJ, where J is not equal to I, for any I. So in other words, you can't get rid of one of the terms without that. So we're going to be talking mostly about these. This one's pretty easy to handle, to tell you the truth, because I can compute each one and see if it's necessary and just throw it out. And I might have different ways of doing it. I'm not talking about uniqueness or anything, but I can do that. And also over here, did I write that down as an exercise? Yeah, the intersection of two P primary ideals is again P primary. So if I have more than one of these that have the same prime, I can just combine them together. Okay, and therefore this gives me an irredundant primary decomposition. This is the goal of what we want. So, but there's a number of things we have to understand a little bit first. But here's an example that I think is a good one to take a look at. And again, we can do this when we take a break. Okay, I'm going to take the ideal. Okay, R is going to be Q adjoin A to D, 4 variables. Okay. And M is going to be the monomial ideal, A squared, AB, B cubed C, and C to the 4th. The first thing to do is to determine, so on this thing, it says, find an irredundant, this is the exercise, not really. Find an irredundant, find an irreducible decomposition of M. In other words, write this in terms of irreducible ideals as an intersection of finite number. In other words, run this exercise. I probably should have put it before saying this. And then after we know just a little bit more, you're going to take the result of that and make it into one of these things. Okay? Yep.
Wait, so this was a primary decomposition. You're asking us to kind of irreducible decomposition.
Yeah, this is A, and then B, but we need to say one other thing first before we can do it, and then turn this into, this is a little bit vague, but basically you're going to use that to find one. Turn this into a primary decomposition of M, an irredundant primary decomposition. Okay. Actually, to tell you the truth, this is a primary decomposition of M, but it's not very irredundant necessarily. Okay. But anyway, so that's a sort of good exercise to sort of get used to the playing around with these things. Okay. Now we're going to be able to prove that this thing is the case. In not before too long, we'll have the exercise that an irreducible ideal is actually primary. I don't think I've stated that anywhere. But that we need a little bit more before that's easy to prove, but maybe it's actually not so bad. But once that's the case, then since we have an irreducible decomposition, and those are all primary, we have a primary decomposition. And then the only thing is can you really go from here to an irredundant one? And that's the exercise, just to make sure that all that stuff is okay. So in fact, we will have the thing that every ideal will have a primary decomposition, which is already a pretty cool thing. There are some, there will be the question of what's unique about it. So question. So actually, let's say soon we will see that we will see there always exists a primary decomposition of an ideal I. Okay. So there will exist. And the question is how unique is it? If I do one and you all do the same one, how similar are they? It's a good question. Well, it turns out they're not the same. Okay, so here's an example, which is an interesting one to work on. This is again an exercise to work on during the break, and it's all monomial. So, but basically the ones to work on in the break, if you haven't done this stuff before, are playing around with which monomial ideals are primary. Do the irreducible decomposition of it, and then do the primary decomposition from that of this thing. And then here's an example of that. Let's take the ideal x squared comma xy. Okay. This turns out to not be. Actually, could this be primary? Well, is this the example we had before? Did I say that? Yes. The radical of this is x. So this is a potentially one. But here's an interesting little thing. We know how to intersect monomial ideals. We've done this before. You take all the LCMs of every element on the one and every element on the other, and then you just throw them all together. And a lot of those are not necessary, but you take the minimal ones you've got. So generators. So this has an intersection of two ideals. So what are the two ideals? And x is a good one, and xy. Actually, that's not quite correct. It's close, but this, if x is in both of these, but I don't see x in here. So x squared is in that one, but not x. Yeah, but x is in the intersection of these two because it's in both of them. So anyone see how to fix that? You mean without that one? Or maybe xy and then intersect with x squared? Yeah, actually, that's an interesting point. What if I do x squared? If I do x squared intersect x, I'll get x squared, right? And then intersect xy, right? What does that equal? That's x squared, comma, x squared y, it looks like to me, which is x squared. That's not quite going to give it to us either.
What you have written first there is no.
Actually, this is correct, right? So if I take this, if I take the LCM, I get x squared and I get xy, which are exactly these two things. Okay. And really what I'm doing is, this doesn't always work, but on this one it does. I'm just factoring out the x and I'm left with, oh no, I see. No, I'm not. That's what we tried to do before and that didn't work, okay? So, but this does work, okay? This one here doesn't work. This is, it turns out, this is an irreducible ideal. And therefore it's going to be primary too, which needs a little proof still. But, and therefore this is a primary decomposition of this. But alas, here's another one. Okay. What about this one? Well, if I take x and I take the LCM with x and all this, I get x squared, I get xy, and I get xy squared. I get x squared, xy, and then I don't need that third one. So I get the same ideal over here. Does that make sense? Actually, it's even worse than that. It's x squared, xy, and y to the m for any m. Is also one. And then it's going to turn out that these are both primary ideals. So that needs to be checked once you have the idea down for that. So this is, so uniqueness is out the window. Okay? Except is it really? So the question is there are certain aspects of it that that are the same. So I have a whole lot of different primary decompositions of x squared comma y. So which ones, what kind of uniqueness do I get out of it? I mean, just looking at this, what's a conjecture for what's unique? Aha, the radical of the primaries is x and xy. And this is x and y too, and that's x and xy. So in fact, uniqueness might include all of the primes, the P1 up to, where did we define it? The P1 up to PR. That might be all, that might be unique information. It turns out it is. And so there is other stuff. All three of these have the same, this x is the same. What's the zero set, by the way, of this x squared xy? Let's just, get back to the basics here. It's this x squared x, so x squared equals xy equals 0 is x equals 0. So that's this, the y-axis. Right? Okay, that's fine. And now what are these things? X equals 0? Well, that's the same thing, right? So this component here, that is this thing. This is what's called a geometric prime, or something. We'll give it another name in a bit. This one, though, is x squared y. That's actually at the origin. This is where schemes come in. So if you're looking at it just algebraically, like looking at zero sets of polynomials, you just see x equals 0. You don't even see this thing at all. It's just gone. But that's because we're replacing this with its radical, which is just x. But if you don't want to do that, then it turns out that you have the intersection of these two things. And really what that is it's a line, and then it's a kind of fat point. It's a little larger than the point xy. So schemes, this is the difference between, this is why schemes exist, okay? Is that to take ideals that are primary decomposition and have both of them appear in the picture. Whereas otherwise, if you just take the radical, you'll lose that little thickness at the origin. But anyway, that's just a little aside. Any questions so far about this stuff? Okay, now we need to switch over the camera again. So the next thing we've done, we know how to compute, at least in the polynomial ring case. But it's important here, so we're going to just recall it. So ideal quotients and saturations. These are completely crucial tools. Before we just saw them as something. And it's actually quite interesting, but here, let me first state what that is. Recall that I colon G, sometimes you put parentheses around it, like that, just because otherwise it gets kind of confusing what you're referring to. This is the set of all H in I. No, sorry. Let's do this right. First of all, let me use the same notation I've been using. This is the set of all F in the ring R, such that F times G is in I. So you scan through all the elements of I. Whenever you see a factorization with G, you just get rid of the G. I mean, you just add the rest of it in. So you cancel out all those things. So this is this. This is certainly an ideal containing I, right? Because any element in there, if once F is in there, I multiply by G, it's still in there. That's fine. So we also have, so note that we have that I is then contained in I colon G. Well, actually, I can do it again. I can do I colon G colon another G, which is the same thing as I colon G squared, which continues on to I colon G to the 100 and so on. Okay, so I have this sequence, and now this is a sequence of ideals. I contained in this, contained in this. This is an increasing sequence of ideals, So our Noetherian, which is our standing hypothesis for the day, that implies that this stabilizes. And we define I colon G infinity. This doesn't mean anything except by this notation. One way to think of it is the union of all these guys, I colon G to the M for M greater than or equal to 0. But then this is also equal to I colon G to the L for some L. Okay, makes sense? So, and this is called the saturation of I with respect to G. Okay, we know how to compute both of these using Gribner basis, yes? No, they're not. Well, for instance, let's take an example.
Mike, can I ask a quick question?
Sure.
There was nothing special about the fact that G was an element here. You could have done this replacing G with some ideal J. Is that right?
Absolutely. Absolutely. In fact, I probably should have done that. A generalization of this notion is if G were an ideal J, I could do I colon J is the set of F such that F times J is actually now a subset of I. Okay. And I can take it still will, we could just take J squared, J to the 100th, and so on. And so we'll get the same thing for the saturation. And in fact, Macaulay 2 allows that that notation also. And in fact, there are times when we want it. For primary decompositions, doing it with single elements is enough. Actually, you can compute it for arbitrary ideals in terms of this. That maybe would be a good ideal example to put down on this as well. So let's so as an example of something like this. This is a pretty simple example, but let's suppose that I is equal to the ideal x times y squared times z to the 5th. One single generator. And now G, I'm going to take to be just y times z. Now what is I? So I is this. What is I colon G? It's everything that you have, whenever you see a YZ in the ideal, you get to divide it out. So I see a YZ here, I get X, this is going to be the ideal X, Y, Z to the 4th. Okay. Now we'll go down. This contains I, that's larger than that. And now we do I colon G squared. Well, that's whenever you have a Y squared, Z squared in the ideal, that gives a Y squared, Z squared. So that is going to be X, Z cubed. I think that's right. We've gotten rid of Y. Do I have that right? Actually, this is Y squared, Z squared. I think that is right. Okay. So do you buy that? So G squared is Y squared, Z squared. I just divide this by Y squared, Z squared, and I get X, Z cubed. And now what can I keep going further? What if I do I colon G cubed? What is it? Anyone want to say? Yeah, just X. And then actually this is equal ... all the same. So this is equal to I colon G infinity. Now, what are the zero sets of these things look like? Yep.
I'm confused why I G cubed is just X, since we now only have 3 powers of Z.
Oh, I see. No, you're right. It's not yet. That is true. So this is not correct yet. Sorry. So what is it?
X Z squared. Yes.
I think that's right. And actually, I shouldn't have done it so high because now I have to write stuff down. So this is X Z and I colon G to the 5th, which is now equal to I colon G infinity, will be equal to X. Okay. So now when you colon with YZ, it doesn't even appear anymore. It's just not going to change anything. So, but what's going on? This thing has the zero sets x equals 0, y equals 0, and z equals 0. And then all of a sudden we've lost, actually it's the same here, but we've lost y equals 0 here. And then we lose z equals 0 as well. So we're eventually getting all of this. And geometrically, we'll be able to say exactly what's going on is that when you're doing the infinity version, at least, essentially you're wiping out all components of some type, but that's exactly what we're going to be using it for primary decomposition.
Mike, sorry. Can I just ask a quick question?
Sure.
This intuition of dividing out powers of G. Well, when you have G cubed, you have Y cubed. You can't really divide that out.
But it's really, you're only looking for things that multiply in the ideal. So it's not the single element that you're interested in. So
Okay.
for instance, which was G cubed? So xz squared, times G cubed is Y cubed, Z cubed. That's equal to x y cubed z to the 5th, which is in the ideal I. Okay, so actually it's pretty, you have to, just doing this really quick like this is probably a bad idea. You have to make sure that it's really equal to this at each point. So if these were not monomial ideals, it can be quite confusing. So you have to be careful. But here's an exercise. Okay, so is this okay now? So this is the notion. We've done this. We know how to compute it. How do we compute the I colon G? We did I intersect G, and then we divided by F, or G rather. And how do we do this one? We added in a new variable T, and we added in the polynomial G times T minus 1, and then we intersected away back to all the X's. Yes?
If we're not assuming that R is Noetherian, which I know we're doing today, but if we're not, how can you do this in Macaulay 2, for example? Like, how do you do this?
You can't do any non-Noetherian ring in Macaulay 2.
Okay.
That's actually not quite accurate. You can do some non-commutative rings, but there you don't get finite Gribner bases. You can only get partial Gribner bases. So it is still possible to say things there, but it's really tricky. For instance, if I look at the union of all of these things, it will never equal I colon G to the L. It will be some ideal, but it's quite hard to compute. In fact, I don't know how to compute it in those kind of cases. So pretty much every ring that you deal with in Macaulay 2, or most of the time, is Noetherian. And if it's not, you have to do some trickery to figure out how to deal with it. Yep.
Is there like a notion of a limit kind of thing? Like,
Sure.
if you're taking the saturation as the M goes to infinity, kind of?
Yeah, I mean, this union here is an ideal.
Yeah.
So I can define it to be that, whether it's Noetherian or not. That's a well-defined object. However, I don't know how to compute it.
Yeah.
So that is a slight issue. So a couple things, by the way, about this. Here, I'm going to remove this little bit here, I think. Here's another exercise. I think it's a good way to think about this in here is that if I is irreducible, then I is primary. And the hint is to use that I colon G infinity is equal to a specific power for some L. Okay. So to show it's primary, you have to take an F times G in it and say something about it. And there's a G to the M. Well, that's actually going to be pretty cool. This is it becomes a fairly simple thing, but it's important to do this if you haven't done it. And I think it's better to have you do it yourself rather than me do it. So we have that. By the way, then this is 1, and then deduce from this, just like I had before, deduce that every I contained in but not equal to R has a irredundant PD. Okay, well, it will already be a PD once this is true, and then you just have to combine things. And then apply this to the monomial ideal above. Okay, so I'm writing down the exercise twice somehow. They're in here, but at any rate, that's what we have. Okay. So now, let's see. Yeah, this is good. Okay, so I want to do a little bit about uniqueness and stuff here, and then have you play around with these notions. If you already know those notions, then I will have you do something else. But I think that probably that playing around with how many of you do not know the answers for some of these things right off the top of your head?
This is in week 1 exercise. Some of those were in week 1 exercises. So we did try them out way back when, but most of this is new. So.
Okay.
But this is good.
But doing the irreducible decomposition of this and getting a primary decomposition of it might be a good thing to play around with. So we're still not at a point where we can write down an algorithm for any of the stuff other than for monomial. Actually, we're at a point now where we can do it for monomial ideals once you do the exercise. But we'll talk a little bit more about that in a bit. But so the question is, what about uniqueness? Of a primary decomposition. And we know that it can't all be unique because of this nastiness. This is incredibly annoying. I gotta say that that ideals that you don't have this uniqueness. I mean, obviously, whenever something's annoying, then that means it's important somehow. But nonetheless. So here is a proposition / exercise. So let's let Q be a P primary ideal. In R. And let's let, I guess I'm using F this time. Sometimes I use F and sometimes I use G. But it doesn't matter. So here's the first one is what is Q colon F infinity? Okay. So in other words, I get to factor out as many powers of F as I want. What is this equal to? This is a good exercise, and in fact, almost a better exercise if I don't tell you the answer. But the answer is in here anyway. So so if F is in the prime ideal P, well, that means some power of it is going to be in Q, although you have to think about that still. And you get the unit ideal. Okay. And if F is not in P, what do you get? Well, you have to think about it, but you get Q itself on the nose. Okay. This is pretty simple. It just depends whether F is in the prime or not in the prime. Okay. This is A. Slightly more annoying is if I do Q colon F itself. Okay. And this has 3 conditions. But this is a good exercise to do also in the project part. So what is this equal to? It's equal to one of 2 things. One, Q colon F. Actually, I don't want to say it that way. It's always equal to Q colon F. It's going to be a P primary ideal in the second case. And it's going to be Q here, which is also P primary. But this one is just going to be a Q colon F. Okay, here's the situation. This is if F is in Q. This is F in P, but F is not in Q. Okay. So remember, we have we have Q is sitting inside of P because this is the radical of this thing, basically. And if F, so where can F be? F can be here, and this is in R. So it can be here or here or here in the smallest possibility, and that's what the conditions are. If F is in Q, well, then Q colon F is equal to 1 because by definition. If it's not, this is the one you have to actually check. And if F is not in P at all, and it's just up there, then you don't get anything new. You just get Q. So what I want to say here is, let's do an, so that's an exercise. So as a consequence, well, let's do two of them. Let's just do, let's apply, suppose that we have I is equal to Q1 intersect dot 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 up to QR. And QI is PI primary. Okay. Then I colon F infinity is equal to what? By the way, if I take I colon F and I have an intersection of ideals, so I should write that down. Before we do that, let's say, first note that I colon F then is equal to Q1 colon F intersect dot 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 intersect QR colon F. And therefore I colon F infinity will also equal Q1 colon F infinity intersect dot 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 intersect QR colon F infinity. Okay, that's a little note. And then we'll say, let's just make sure we understand this. If I have a element in here, GF is equal to, is in I. Well, if GF is in I, then it's in every single one of these things. So G is in each of these ideal quotients. And then the other way is just the same. So if I have one element that's in here, then F times it is in each of the Qs, and therefore it's in the intersection of them. So these things are straightforward, but they're pretty cool that ideal quotients interact quite nicely with intersection of ideals, at least in this first part here. Okay, but this tells us quite a lot because if Q is here, so let's suppose then the note is that if, well, what is it? What is I colon F infinity? If it's the intersection of all these things, each one of those is either the unit ideal, which is everything, so we can ignore it, or it's equal to the rest of them. So this is the intersection over all of each, and this is equal to the Q sub I, where P sub I where F satisfies what with respect to P sub I? Yeah, so I want to say that Fi is not in P sub I. Sorry, F is not in P sub I. Okay. So let's just think about geometrically. What does this say? If I take the zero set of I colon F infinity, so first of all, let's put this over here. Actually, before I do the geometric stuff, let's do an example of it. So an example. Let's suppose that I is equal to x, y, x, z, like this. Okay? Contained in R, which is k of x, y, z. And again, I forget, I get going, I stop using angle brackets, but it's just the ideal. And now I'm going to take F equals, it doesn't matter which I take, but let's take X. Okay. What's the zero set of I look like? It's the set of all, first of all, it's the set of all. Actually, that's a good question. What is the zero set? of an ideal I. Okay, we have not really, I've been sort of assuming that you have it, but we haven't really needed it precisely or anything. We still don't. But in fact, I'll say it precisely later, but it's the zeros of this in 3 space, right? So I don't want to do that. I want to just say pictorially what it is. Well, it's x equals 0. So if this is the coordinates and this is x, y, and z, I should have chosen a different one, but this is equal to the x equals 0 is the yz plane, right? And then what's the other one? It's where y equals z equals 0. It's the x-axis. So I'm just going to do it like this. So this is this is y equals z equals 0, which is the x-axis. Okay. Now what I want to do is I want to consider what so I here is equal to the ideal generated by x intersects the ideal generated by y and z. This is a primary decomposition. This is a nice this is a radical ideal. I didn't actually say that that means that these will be primes, but at any rate, we have this, and a primary ideal like this is you really think of it as the zeros of I are the unions of these things. That would be one way to think about that. And in fact, that's what it is. The union of x equals 0 is this thing, and then the union of that. Okay, so let me say V of I is equal to the 0 set of x union the 0 set of y and z inside of 3 space. I have a union here. That's the ideal is the intersection of these things. So ideal intersections turn into unions of 0 sets. Okay. So we have this, and the whole point of a primary decomposition is that it breaks up your thing into small. Geometrically, it really is breaking up into smaller parts. Ideals, it's a little more of this weirdness that it's the intersection of things is giving it to you. But geometrically, it really does do it, and that's where all the intuition should be coming from. Okay, so now we can say what this thing is geometrically. This is equal. So the 0 set of I, for instance, let's say it's x1 union ... union xr, where x sub I is equal to the 0 set of q sub I. Actually, that would also be the 0 set of p sub I, right? If we're doing it in this naive way. But then what is the 0 set? Then the 0 set of I colon f infinity is equal to what? Oh, I didn't actually do it over here. Shoot. V of I colon, which one was I going to take? X infinity. Turns out this is the same as I colon x. What is this ideal? I colon x infinity? That's where you wipe out, if you see x and wherever you get it, you get to divide by it. This is the 0 set of y and z, which is this thing here. And so basically this is wiping out some components. Which components is it wiping out? Yeah, this is sorry, y equals z is this line. So it's wiping this out. But why is that? What it's doing is it's wiping out any component. So if f is not in pi, that's the same thing as saying that the 0 set of pi is not in the 0 set of f. Okay, actually, let me so this is equal. I want to say that this thing is going to be the union of the xi's, where the 0 set of xi of that thing is not contained in the 0 set of f. So in other words, if I have f equals x, that's a single polynomial. And what this is doing is it's wiping out, when I take colon, I'm wiping out everything that's supported on that, on x equals 0. So, so I should probably say this a little better. And then we're going to, so you might, if you could switch the camera, if it's not switched yet. So V of I colon f is really equal to the union of the components, the irreducible components, This is, okay, I shouldn't use that word here. This is the irreducible in the geometric sense now. The irreducible components, V of Qi, so that's Xi. The union such that Xi is not contained in the zero set of F, which is a hypersurface. Okay, so basically, so here's a situation. Suppose that this is F equals 0, i.e., here's F equals 0, and now I have the following. I have this guy here. That's a line. Let's call that x1. And now I have a curve in here. That's x2, and I have some points in here. That's x3, that's x4, and that's what I have. Okay. Oh no, let's say we have another point outside of the plane, x5. So the zero set of I, we don't know what I is, but the zero set of whatever ideal it is going to be equal to x1 union x2 union x3 union x4 union x5. Do you all see that geometrically? So I have a curve. That's x2. I have this line x1. I have a curve inside of this inside of this hypersurface, and I have x3 and x4, and I have x5 are just points. Okay, so this is this thing here, and now I want V of I colon F infinity. So which ones go away? All the ones that sit on F equals 0 go away. So it's kind of weird. It's not like you're keeping the ones on F equals 0. It's the opposite, which is completely annoying sometimes because you want to zero in on F equals 0. This is not the way to do it. Okay. So this thing here is going to be x1 is not contained in it. x2 is contained, so it goes away. x3 is contained in it. x4 is contained in it. They go away. x4, so an x5 is not. It's a point, so then it stays there. So it's just wiping out all the ones geometrically. Yep.
Do we lose anything at the intersection of the plane and
So like no. So actually we do. So so really what's going on here. So one way to think about this maybe this is even a better way to think about it, is V of I colon F is equal to V of I minus the zero set of F. Okay. But this is not closed. You got rid of, if I take this thing and I reduce that, I have a open thing here where I got rid of that point. But I close it up, I take the closure of it, and it puts it back in. So yeah. If I is a radical ideal, it doesn't matter. It's going to be the same thing. But in any case, this is what it is. So the great thing about ideal quotients is they mean a lot when you're dealing with components of a variety. You have a whole bunch of things, and you want to figure out what there is here. You want to get rid of some. If you happen to know where the bad ones are, you can just do a colon, and that clears it out for you. Unfortunately, sometimes you want the ones that are on F equals 0. Good luck figuring that out here. Okay, so we have to do more work. But this is probably a good way to think about it. So because if I have a component here, I'm wiping out F equals 0. If it's all completely contained in there, it will not appear in the closure at all. So it's just gone. Okay, this is all very interesting. When I remember when I was an undergraduate, my mentor, who was Graham Evans, they were reading through Nagata's, or he had done this actually many years before, but Nagata has a book on local rings. And there's a huge amount of stuff on properties of ideal quotients. And it's just formula after formula without any indication of what they are geometrically. But as soon as you understand what they are geometrically, all of a sudden, all of these formulas make sense. And Nagata knew all that. He just didn't sort of write it all down, I think. least I think that you knew about it. But once you understand that they're important, then all of a sudden you're interested in some of these formulas, whereas before maybe not so much. Okay, I think right now we'll take a 10-minute break. It's 11:20 almost, not quite, but almost. So at 11:30, let's come back and we'll work on some of these exercises. And then we will get back together and go over some of them exercises. And then we'll move on and do some more primary decomposition after that. Okay, cool.
Mike, can I ask you another quick question? Sorry.
Certainly.
In this last picture you've drawn, are we doing this? We're doing this affinely, right?
Yes, but actually it doesn't really matter. You could do it projectively as well.
Okay, so I guess my question is, this is all pictorially. I understand you have to take the closure, but pictorially, it seems like the point of intersection between the line and the plane has multiplicity 2. So when you remove a copy of the plane, that should just remain with one multiplicity. So you shouldn't technically need to take the closure.
So actually,
what am I
that
missing?
isn't quite correct. That actually has multiple, you know, it's a transverse intersection, so it sort of has multiplicity 1. If you but I guess I see, because if you take a curve and it has 2 crossing points, you would say that has multiplicity 2, even though it's a transverse intersection. So that is true what you're saying. But it's not the case here that that doesn't have anything to do with these ideals. That has to do with the ideal if when we're intersecting these 2 ideals, x1 and x2, then it makes it, that's different. And then we do pick up
But you are intersecting those ideals. If you're taking the union of the geometric object, that's.
Sorry, I meant intersecting the varieties.
Okay.
Okay. But actually, here it doesn't really matter. Nonetheless, suppose that you allow yourself to be thinking scheme theoretically, and that point here is a fat point of intersection somehow. Okay, then the I colon F infinity will still wipe it out. But if you just did I colon F, it would probably still remain. It might still remain.
I see. Okay, thank you.
Okay, it is time for us to get started. So, so should we talk about? So does anyone want to say anything about it, or should I just? About the types of monomial ideals. Let's do that first. So monomial ideals, yeah. So we already had that maximal. It's pretty clear, I think. What are the maximal ones? Yeah, so this is in n variables, right? So that's that. And prime, what are those? Yeah, xi1 up to xir, basically, right? And because as soon as it includes xi times xj, and xi and xj are not in there, then you're out. Then that's it. Okay, how about irreducible?
Generated by pure powers of 1.
Yeah, so this would be like xi1 to the a1 up to xir to the ar. And why is that? Well, if you have any monomial that has 2 different variables in it, you can say you have an x to the a, y to the b, and other monomials, right? So this is what you were doing, I think. So this is equal. Let's call this j here. This ideal j. We can take x to the a plus j, and y to the b plus j. And this thing is going to equal, intersection of these 2 things. I should actually be asking you this. This is not the way I should be doing this. So, yeah. So forget what I just said. So, so why is this true? Let's get rid of this for the moment. So why are these the irreducibles? Those are irreducible, right? So one needs to prove something about that. But if this, there's actually several possible things, but let's suppose that the intersection would have to be of two monomial ideals. That's sort of what we were talking about. I think you might have to actually prove something there. But at any rate, then in order to get the intersection of two primes to be something like this, that means you have to have this has to be the LCM of ones on both sides. But if that's the LCM, that means one of the two has to have this one in it at least. And actually, that's going to be true for all of them, probably. I think that one could probably make a proof like that work. But what if it isn't like this? What if it has a something that is not a pure power of a variable? Like suppose I have x times y to the a, b, and other monomials. But x to the a and y to the b are not in there. Yeah, you can just, since you can do x to the a comma the others, like that, and y to the b comma the others. And if you think about it, so the others, LCM of the others with the others are just give you the things you have. And in the x to the a and y to the b, you're going to give you x to the a times y to the b here. You're also going to get xa. Well, anyway, you're going to get the others, and you're going to get x to the a, y to the b. So this thing is equal to this basically because it contains all the generators of this. Could this be larger actually than that? Actually, why not? So if one of these monomials is z, then this would give me an x to the a z, and I might not have an x to the a z here. Actually, now I'm a little worried about that, but about my proof. But basically, these are the irreducible ones. We're gonna have to think about a good proof of it. The proof I was just thinking of.
I'm sure that they are the same.
Or they think these are the same? So why is that? So the question is this equal to this question mark, right? Let's say that's the left-hand side and this is the right-hand side. That's what I thought too, but then I all of a sudden got worried about it.
All right, I have a question. Can I ask you something?
Yes, please.
Yeah, what is the problem with this equality? I think it's pretty straightforward. They're equal. Just take all your LCMs, right? On
Yes.
the right-hand side. We know
But,
how.
I see. You're right. X to the a and others is going to be larger than others, which is
Yes, like the
this is
LCM
just obvious.
cancel
You're
out.
right.
It's very
Okay,
obvious.
good. Thank you. So this is just definitely an equality. Okay, good. I just got confused. So so this is equal to this, and consequently, whenever you have something that can split, you can just split it, and then you're left with these, and those are irreducible. I have to think about exactly why. What about primary? Well, so the other one was radical, and those are just the ones when all the generators are all have exponent ones on all the monomials. So so as soon as you have a higher power on a minimal generator like x squared, it's not radical because you can take this square free part and then some power of it will be in the ideal. So radical, but what about primary?
Compute power of variables and monomials that involves just the variables in the previous variable.
Yeah, so suppose that it's p primary, and the p has to be one of these things. So it's xi, say xi1 to xir, and then q. So this is q is p primary. Q has to be a monomial just in these things by themselves. If you had one of the other ones in it, then it would just fail the primary test. Because if I had some monomial in here times another variable, then that one would not be in it. But the other one, so no power of it is in there either. So so that the only way that you can do this is if you have some monomial in these variables. So this is equal to a monomial only involving xi1 up to xir. So e.g., for instance, x squared xy y squared is xy primary. Actually, so is that x squared xy y to the m is 2. But as soon as I have an x squared xy y to the m y cubed and xz or something like that is not, because the power of z, there's no power of z in this ideal, and x is not in the ideal because if it was, that wouldn't be a minimal generator. But if that's a minimal generator and this thing doesn't, that means that either that's in the ideal or some power that's in the ideal, but no power that's in the ideal. So you can also tell by looking at the ones that have actually are pure powers in it. The radical of this will always be just the ones with pure powers, and so you can easily tell what the radical. This has radical xy, but it's not primary because of that z. So that's monomial ideal land.
You're saying the generators for Q will be monomials only involving xi1 and xi1.
Yeah, so if I take any monomial, for instance, in just x and y, then that will be xy primary, and no other such thing will be, as long as it's a minimal generator. I mean, like I can always take x, y, z, but if I have x, y in there, it doesn't matter whether I will have x, y, z in the ideal, just not as a minimal generator.
But also, like, don't we also need there to be pure powers? Maybe you said that already.
So it's going to be p primary, which means that how do you tell what that is? You take all the square free parts. So that's going to give you an x and a y, and then that one will be all the other ones that involve x and y will be gone. But others here you would have x, y also. But anyway, you can tell then what the variables are. If the square free was not that, it was x, y, and z times w, then it's not primary at all, because z times w, you don't have either z or w in the ideal, or you don't have the power of them in the ideal. So monomial ideals are kind of nice this way. Irreducible ones are really good. They're just like this, and then primaries are where you have all of them. So one of the questions was, is an irreducible always a primary? And from a monomial point of view, you can see that everything of this form is of this form, where where all the monomials only involve those things. It's just a little simpler.
Shouldn't we ask also that the pure power of xi1 and blah blah are in Q for the P primary, since
That's what
the radical of Q is P, so a power of x.
Yeah, that's right. Oh,
Q1
wait,
should
this
be-
absolutely, and the radical of Q has to equal P. In other words, you have to have some power of each of the variables. Absolutely. Sorry, I didn't realize what you were talking about.
Yeah. Sorry. Yeah.
So, and ideal quotients are easy. I mean, monomial ideals are great as far as understanding these things. Unfortunately, they're sort of really easy when it comes to what we're going to have to be doing for other ideals. Did you want to go do that? So the other issue is, in general, not for monomial ideals, although here we can see it. If it's irreducible, we want to show that it's primary. And so then there's this key lemma that's in page, it's further back in than I planned on, and I moved it back further by accident somehow. and not by accident. I thought I didn't need it. So, but I think it really helps with this thing. So do you want to do it or?
Yeah.
Okay. Okay, so you can put that in, I don't know where you're gonna.
Okay, that should do.
Do people online here?
Hello, testing. So we're going to prove that for I guess we're doing proper ideals of R. If, should say also, and our running assumption is that R is Noetherian. If I is irreducible, then I is primary. And for the proof, we'll prove the contrapositive. So assume I is not primary. Make my height adjustment. Then there exist, I'll say, F and G in the ring such that F is not in I and G to the M is not in I for all powers of M.
G is in on.
Oh yeah. I wasn't looking at my notes, but FG is in I. Thank you. So we'll show I is reducible. And so we need to show that it is an intersection of two ideals which are not equal to it. Observe that from before we know that I is contained in its saturation with respect to, I'm going to take G, and the saturation is equal to the colon with respect to G to the L for some L. And also, I guess the colon with respect to G to the L is not equal to I. Trying to think to myself, well, why is that? What's the easy way to see that? I is contained in this.
That's right. So, so you have F is in there in any case.
Yeah, that's right.
So
F
is in that.
is in here, but it's not in I. Because F is in I colon G to the L, because if I hit it with G, I wind up in I. So if I hit it with G to the L, I wind up in I. And not in I, so yeah, so F is in the colon, but not in I. And now also consider that the sum of I and I'll just do G to the L. This is not equal to I because G to the M is not in I for all M. And then the claim is that I is the intersection of these two ideals, the colon with respect to g to the L, and the sum with the principal ideal generated by g to the L. Maybe I will, yeah, I'll move over there. Stay here though. Okay, so proof of this claim. So the forwards inclusion is immediate. We know that I is contained in its colons and I is contained in this ideal sum. So this inclusion is immediate. And now we'll prove the opposite inclusion. Assume that F belongs to this intersection, the intersection of the colon with respect to g to the L and the ideal sum I plus the principal ideal generated by g to the L. Then we may write, since F lives in this ideal sum, let's write it as a sum of elements from the ideals.
I just wanted to say you're already using F for something else, but okay.
That's super true, thank you. Let me not use F then. So, well, I was gonna use H over here.
Okay.
Yeah. Do I ever use this F again in my proof? No, I think not. I'm gonna call this A. I'm retconning my proof here. A, because it doesn't come up. In my proof, I used A and B. Okay, now I'm free to use F. Thank you for pointing that out. Okay, F looks like G plus B to the L times H for some G belonging to the ideal I and some ring element H. Okay. Or-
Sorry,
Yep.
what's B?
Oh gosh. Should be, okay. I'm screwing myself up because I use different labels in my proof. So G is the thing that I'm coloning by. And this is now gonna be B. So B is now, I should have just done what I wrote already. Okay, now I'm okay. F is an element in this intersection. And it looks like the sum of something in the ideal I plus G to the L times a ring element because G is the thing that I'm coloning by. Now I'm good. Now my labels are square. Okay. Since F belongs to the colon ideal, I colon G to the L, we have, if we hit F with G to the L, so that is G to the L times F is G to the L times B plus G to the 2L times H, and I wind up in I. But since this is in I, and this is in I, but then G to the L times F minus G to the L times B, which is G to the 2L times h, this is in I. So h, if I hit it with g to the 2l, I wind up in I. So h belongs to the colon with respect to g to the 2l. But we know that L was the point where the saturation stabilized. So this is just equal to the colon with respect to g to the L. So g to the L times h is in I. And hence F is the sum of two things in the ideal I. F is B plus G to the L times H. So it's in I. So my claim is proved, and therefore I is reducible. That's it. Hooray.
Awesome. Almost exactly the proof other than the naming that I was thinking of. Yeah. Okay, so we have 5 minutes. I don't know if there's a whole lot of time to actually do much in the 5 minutes. I do want to, I would like you to take a look at this though, because and as a homework, go through and understand the stuff. Do the monomial ideal primary decomposition that we didn't do. Try it in Macaulay too. Do it all of the stuff up through. If so, one thing we didn't define was what a minimal prime and an associated prime are, but the definition is right here. So what I would like you to do is do that, and what we're trying to show is that the set of minimal primes and the set of associated primes is well defined. That those are the minimal. Yeah, that those are the primes that occur essentially in this thing. So take a look at that. We will probably start with that, but I'll do it very quickly next time. The simplicial complex stuff we will do next time. And then we're going to start in on the actual honest to God algorithm that is the way that we do these things. It's kind of interesting. There are some special cases that are not well implemented, and we'll talk about those as well. But first, we'll do the main characteristic zero version of it, or the perfect field version of it, and then we'll talk a little bit about that. So we'll have to. What we're going to do is, besides, and now we're almost done with the sort of the understanding what a primary decomposition is and the parts of it. Once you take a look at that bit about the minimal primes and the associated primes. You can also read about all of these sorts of things in like a T. McDonald. There's a few other places I might put in a few references in here as well. And then we're going to do this algorithm is really, it's a pretty good one actually. I like it. It's due to Johnny Traeger and Zacharias from in the 1980s, but no one could possibly run it then because none of this, it required so many Grosvenor basis computations at the time that, and since one of them took all of your time, it was impossible to run. And also needed good factorization algorithms. So we're going to talk about that. But it turns out that when you're actually doing this stuff in practice, if you just go to the hard algorithm, just hit it with the algorithm, the full algorithm, it just is very, very bad. Instead, you almost always want to do it some sort of divide and conquer. Well, we're going to figure out what that means, but basically you want to find easy ways of splitting the ideal first, and then you do that as much as possible, and then you only go with the big guns at that. Hopefully those are now small enough because somehow things get simpler when you go to the components of it. Hopefully those are simple enough that the algorithms will actually work. And but this used to be an interesting point because like singulars, primary decomposition a long time ago was really so much better than Macaulay 2. And I was trying to figure out what was it. They had a few good, well implemented things, so it could have been that, but it turned out not to be that. It turned out to be that they were doing all this pre-processing and getting rid of simple cases. We were just hitting it with the whole thing, which turned out not to be a good idea. But anyway, so we're going to have to, there's going to be 3 things we have to do. We have to figure out what those things are. We have to figure out the base case, which is going to be 0-dimensional ideals, which are very cool. It's almost just linear algebra stuff. And then we're going to have to find a way of dropping it down to 0-dimensional. And that's where this formula will come in, basically. If we do it right, this is going to essentially be doable as a 0-dimensional thing. And then we're going to have to, that'll be some inductive kind of thing. So we have various things. The trouble with this, this is an awful thing to do, by the way. For components, if I do add I to that, I might have a handful of components. When I add that power in, all of a sudden it can fracture and have huge numbers of components. But what happens is that when you do the whole intersection, you don't need most of them. So they're redundant. And so redundancy, keeping redundancy under control is part of the big problem here. So we're going to have all these little, it's going to be juggling lots of things in the air, and we'll just see if we can get it to go without dropping them all. So anyway, we'll do that next week. Remember, there's no class. There's this the Women in Commutative Algebra conference here, but then the next week after that, we'll do that, and we'll spend the whole class on that. So I would recommend going through this and then just going over again, getting comfortable with primary decompositions, maybe looking over what's in Tia McDonald about it and things like that. Okay, anyway, enjoy.